her degrees from applied mathematics from Moscow, Lomonosov State University. She is a full professor of applied mathematics in University of Ostrava, Czech Republic. She is the author and co-author of 3 books in mathematical principles of fuzzy sets and fuzzy logic. She published around even more than 200 papers on multivalued logic, fuzzy approximation, fuzzy relation equations, and image processing. And she is in the member of editorial boards of the journals Fuzzy Sets and Systems, Journal of Computational Intelligence, Iranian Journal of Fuzzy Systems, Journal of Uncertain Systems, and she has more than 7,000, even around 8,000 citations from Google Scholar, and she has an ASH index of 40. Please welcome Professor Irina for your speech. And her speech will be on extreme learning machine, a new machine learning paradigm. Okay, I think now it is working.
Okay, so yeah. Good morning to everybody. So thank you very much for the nice introduction. Yeah, actually, I learned that I shall update, because so some bibliography, is changing. But anyway, actually, this is my third Infus conference, and all the time I enjoy Infus family, as Professor Cengiz called this today, and I'm happy to be again with you. And so, first of all, I would like to express my great thanks to Professor Kahraman, who invited me and who actually supported my travel and so my visit here. It's my great pleasure to share with you some actually new results in the direction which now, in my opinion, is very hot discussed with colleagues. This is, in a certain sense, theoretical foundations of machine learning and especially neural network computation. The title of my slide is slightly different from that which is announced in the preceding book, and so I will be focused on this type of the discussion and of the presentation. Okay, so I will show you. So I will start with this motivation. And so please, oh, thank you. Is it better? I think so, yeah. Okay, so I will start with the motivation. And so please, try to listen to me, and after that, to read, because, it's difficult, I know, because I was also a listener of Professor Katpshik talk, and I tried to combine, reading and listening, and it was not an easy problem, so please, first listen and then, read when also I read. Okay, so, first of all, the main question, why we should trust in the neural network machinery? Because now we are living in the situation where machine learning and especially neural networks of various architectures, they are everywhere. And actually, if you are doing applied research, and if your research is not supported or is not compared with results that can be obtained with the help of neural networks, it is practically not accepted by any journal. So therefore, we shall really understand what is going on, why this machinery is so helpful, is so, and let me use this word, is a bit aggressive to us. Actually, it forces us to learn things that they provide. And this is something like, so learning foreign language, because a lot of things is formulated in the language of machine learning, and therefore, actually, we learn this language, so we know a lot of terminology. However, because we started working in this field, in this area, later than the people who just started working at the beginning, for us, we take these things a bit, so with a certain reservation, let me say. And actually, the situation in this field is as follows. we know how it works. We know how computation can be made with the help of neural networks, actually, yeah, as I said, with various architectures. But it is difficult to answer the question why it is so helpful, why it is so efficient, yeah? Because actually this requires, yeah, to understand the underlying theory. And this theory is not I mean, widely available, yeah? Of course, there are many textbooks, but as I said, yeah, all of them, they actually have two parts, yeah? One part is theoretical, and this is very far of computation, and another part is computational, and there is practically no visible connection with the theory, and therefore this is a gap, actually, yeah. So we respect, of course, because nothing else available, but actually the gap should be filled. I cannot say that, yeah, so I will, yeah, do this during this talk, but I will try to, at least, yeah, to approach, yeah, to combine things together. I mean, learning theory, yeah, and so the neural network computation machinery that is based, yeah, on this learning theory. Actually, we will be focused, yeah, on two problems, yeah, that are connected, yeah, with learning, and they are classification and regression. Probably first regression and then classification. Okay, and so we, yeah, so have put in our heads here the question: why should we trust machine learning? I am not successful, yeah, actually, if I press or, yeah, but we are far from, yeah, so, okay, so now I managed, okay, so thank you. You know, so yeah, as I said, we will not cover, yeah, all problems. We will be focused on the so-called learning from sample, yeah. And, you know, so before we start, you know, some with explanation examples, we shall formulate the problem, yeah, and the problem will be a bit narrow, yeah, than we probably used to have. Okay, so in this case, yeah, I will read. So what we are given? We are given a training set, yeah. Normally it is finite, so we are given a set of data set pairs, and this set is called a sample. Somebody? Somebody is speaking in parallel with me, yeah? No problem. Okay. Yeah, no, it's okay. But you know, so yeah, now I would like to show you my so this slide, because this is important. Here you see the problem which will be focused on, yeah? So actually, once again, so we are given a sample. Sample is a data set of input-output pairs, yeah? You see them. The notation of the sample is Z. Again, the pointer is not working, but okay, I will read. No, it's yeah, not important. Okay, so you say a sample, yeah. By the way, I mean the principal notation is highlighted, yeah, in another color, yeah. If you can, yeah. So there is no pointer, yeah, actually,
Yes,
yeah.
this one.
Or I do not see it.
I know, but actually I don't know.
Okay, so
work it out.
Let's continue without it, yeah. Okay, so yeah, then where is the problem? Yeah, the problem is that we shall connect these points because they are discrete actually, yeah, and we are looking for a function, yeah, which connects these points, yeah. But actually, yeah, we understand very well that there is no only one possibility how the points can be smoothly connected, yeah? So there are plenty of functions, and therefore this type of formulation is the so-called ill-defined problem or ill-posed, yeah? Because this problem does not have a unique solution, and therefore we shall specify the set of functions which we somehow would like to associate with this sample. Yeah? And this set of function is called as a hypothesis set. Yeah? So here it is denoted by capital H, calligraphic H. Yeah? And then, so we have set of functions, we have points. So what is the problem? How we can pick up a very good, so in a certain sense, an optimal function that characterizes all these points from our sample. Yeah. To do this, we just assign the so-called empirical error. So this means that we estimate the difference between the functional values at the given input points, and the known output values. And so here you see, so this is the so-called empirical error, and we are trying to minimize this error. Of course, the immediate question is the following. Okay, if we fix some set of functions, and if we have an error and we want to minimize, how we are sure that there is a function unique that minimizes this error? We are not sure, actually. So again, but this is an important question. So without it, we cannot continue. Luckily, we have an assertion, that says us if our set is compact in Banach space of continuous functions on X, X is our domain, then a function empirical, it is named. Then there is a function fz minimizing this empirical error. So this means that solution exists, but actually we are not sure that it is unique. But in any case, so if it exists, we can pick up any solution. And so this is good result. However, do you see how many assumptions this statement has? Actually it should be compact, Banach space, and blah, blah, blah. And so, so people, are boring, really to analyze whether in their concrete situation, so all assumptions are fulfilled. Therefore, of course, mathematics helps in this point. Okay, so now, if we manage to solve this problem, then actually how we can use, why we are happy having functions, because we can use this data set, what we are given a sample, for so-called predictions. This means that when another input point comes, then using our hypothesis set, which we call a model, we are able to compute. But of course, because the function is artificially associated with the data set, so we do not call this, computation, precise computation, whatever. We call this prediction because, so very often, we also supply this result with some estimation of probability. But we will not speak today about probability at all. And then, so this is prediction actually, So, okay. And then we should be somehow required to explain why this prediction, is good enough, actually. And so we distinguish between trust in prediction and trust a model. So we trust a prediction if somebody explains. For example, I just explained you how prediction is made, and you believe me that, provided that the complicated conditions or assumptions are fulfilled, that we trust the prediction. But then another question connected, probably the more important, why we trust a model, because, so I tried, to show you that, okay, so we will pick up a hypothesis space, actually, of functions, and nobody asked me, about that, okay, so, which space, actually, you prefer to pick up, or I don't know, so you prefer to work with, and this is really a very complicated space, complicated question, and there is no unique answer. Actually, mathematicians answer this question using, say, simplicity of model. So the more simpler the model, taken for the hypothesis space, the better, actually. So this is explanation. However, if we follow all these steps, yeah, we are not guaranteed that the computation made, yeah, is trustable, yeah. And this is example, yeah, you know, so it is taken from the paper, yeah, with the same title, Why Do I Trust You, yeah. And where, so the example, yeah, is as follows, yeah. So some pre-trained neural network is used. So I will show you later the name of this neural network. I forgot it. Yeah, and then additional information. So additional inputs was used for extended training, and these additional inputs were images of animals, dogs and wolves, actually. Yeah, and for dogs only huskies were selected, and for wolves, you know, so yeah. And then, you know, so prediction. So this network was again trained, yeah, with additional images, yeah, and then the new input comes, and so we expect, yeah, to obtain an answer. So, but when the input of husky, yeah, was somehow put as an input to this additionally trained neural network, the answer was wrong, actually, yeah. It was classified this image as wolf, not a dog, yeah. Okay, and now so we have actually, yeah, as we said, yeah, so how we can explain this bad prediction, yeah, what, where is the problem, yeah, so either we somehow go outside of the domain, yeah, or a model is bad, actually, yeah. And then after making analysis, yeah, so people, yeah, came to the answer that actually the training was good. However, the classification was made, yeah, not on the features extracted from images, but from the features, yeah, from the background, actually. Yeah, so I will show you the explanation. Yeah, so all images of wolves, yeah, were taken with the background of snow, and all images of dogs actually did not have this background. And therefore, when a husky dog comes together with snow, yeah, so the answer was it is a wolf, yeah. So this means that, yeah, the whole machinery, very complicated. This is deep learning, yeah. Actually, yeah, Inception, yeah, neural network. Now you see, yeah, the name of this neural network, yeah. So so when this machinery was activated, yeah, actually it produced a bad result, yeah. And where is the mistake? Mistake is in a model, yeah, actually, yeah. So the model that is based on classification according to significantly different features, yeah, and it didn't take into account features that are similar, yeah, because probably the threshold, yeah, was high enough. Okay, so yeah, this example only shows that we shall not believe, I mean, without thinking to the neural nets and to the machine learning, which is actually the main procedure how to activate a neural network to give us proper answers on our problems. However, you know, so yeah, it is easy to say that we shall be careful, yeah, with neural networks, but how we can be careful? Yes, yeah, so what shall we do as users? Yeah, how we can? Yeah, because you know, so yeah, we have no access. This means that, yeah, it is better really to understand better, yeah, the process of learning and how this process is realized by neural network computation. And this is actually, yeah, the purpose of this presentation. Yeah, so this is the explanation which I already explained. Yeah, so our focus, yeah, of this talk, yeah, is, yeah, so you know, so yeah, I selected, yeah, a very simple model, yeah, because it is easy to explain, but however, we can then, yeah, generalize this model to networks, yeah, which have more complicated structures. Okay, so yeah, so we will be focused on so-called supervised machine learning, yeah, that is executed by feed-forward artificial neural networks. Yeah? And actually, we will use the abbreviation SLFN. This is single hidden layer neural network. Yeah? And so you will see this abbreviation, I mean, in my slides. And actually, our focus on the 4 questions, and we will answer them at the end of my talk. Yeah. So the first, what can be learned? What? Yeah. Then, how does learning relate to random selection? Yeah. So of parameters. Yeah. How many neurons do we need for successful learning? And how does assigning model parameters affect proper learning from samples? Actually, what is important? Every model, yeah, is made with the help of parameters. Parameters are extracted from data. This is the so-called data-driven modeling, yeah? And therefore, we shall understand, first of all, semantics of parameters and their connection with data. If we do not understand, so yeah, I am against of taking neural network as a black box, because black box, yeah, actually does not have any model. Yeah, it respects only input and output, and we do not see inside. Yeah, but I would like to look inside, and I would like to know semantical meaning, yeah, of all of parameters that are included in this simple model. Yeah, and what are they? So let us look at the model. Okay, so this is the simple so-called SLFN. Yeah, as I showed, this is abbreviation for single layer. Yeah, actually this is one hidden layer. Therefore, it is single. But actually, this neural network has 3 layers: input, hidden, and output. Yeah. So the structure is here, and I will not explain because so everybody now knows this structure. Yeah. I will show you only the simplest case where this neural network has one input. Yeah. So so just thanks to this one input, all notation will be simpler. So this is the same neural network, but with a restriction to one input, as you see, yeah. Otherwise, the hidden layer, yeah. So hidden layer, yeah, as you see, is consisting with neurons. Actually, we have, yeah, some parameters are important, yeah. So we have here neurons. The amount is capital N, yeah. So this neural net has N hidden neurons or nodes, yeah, if you prefer. And actually, because of one input, each neuron has also the corresponding weight factor and corresponding bias parameter. So these are parameters, actually, yeah? So remember, so we are thinking about the meaning of parameters. So we have input weights to neurons, and also we have output weights, and these output weights, they connect neurons with output, yeah, again via aggregation. Okay, so, and now this is the important fact, yeah, okay, so if our computational model is like I showed you, then actually how we can characterize, how we can represent functions that are computed by this model, yeah? And here you see, so the expression which has one star, yeah? Label, yeah, shows the computational process. And actually, so you see, yeah, probably label, it's written here, yeah. So we have actually, yeah, this model is for multiple inputs, therefore inputs are denoted using vector denotation, means in bold, yeah, but in any case. So inputs are xj's, as you see, they are connected with weights, and then a bias is added, yeah, and these parameters are input parameters for a neuron, yeah, and each neuron has the so-called activation function. I didn't spoke about that. This is sigma, and actually it is assumed that sigma is unique for the whole neural net, yeah, so at least at this configuration. Sigma is not changed, activation, yeah, and then when, this computation is done, the weight that connects, yeah, the output of neuron with the total output, so is denoted using W2. Yeah, so we have 2 weights, inputs with 1 and outputs with 2. Yeah, actually these are parameters. So can you tell me their meaning? I mean, with respect to the input data. Yeah. Yes. So we just so no meaning is assigned. We know them as weights. Okay. So weights is very general. Yeah. But now we will try to analyze. So what is the meaning of these weights? So our goal is, as I explained, to minimize the empirical error. So this is the repetition of the previous slide, as you see. And so because of the computational model, which is really, so network, follows the computational model, it cannot jump out, and therefore the hypothesis space of functions, which is immediately associated with this way of computation, is given here. It is denoted by again this H, capital H, and parameters, indices, I will not read them, and then the expression which we saw above is repeated. So this means that we will be looking for functions exactly from this set, actually, and the function which minimizes the error, will be our winner, Actually, what shall we do? We shall find parameters, and now just think about, is it possible really to do it in a unique way? And the answer is no, because there are more free parameters than the input data, actually. So we have input data only some capital N, say, couples of input-output, but then we have weights, we have bias, and actually activation function, is parameter, actually, And so we have more unknown parameters, and therefore, in this case, the solution cannot be unique. In order to make it unique, we shall specify something. So this is the list of algorithms that actually help us to perform learning. But in any case, let me continue. So okay, so the first question is, so we have family, hypothesis function, that every neural network of this architecture actually computes, So the first question is, how big this family, And the answer was given, by the theorem, which, you see here, and I will not read assumptions, but it has been proved that, what is important? It is important that, first of all, the activation function is fixed beforehand. It is called as discriminatory function. Sigma is discriminatory. So what is discriminatory is explained, in the above part, of this slide, So actually the purpose is to separate, 0 from 1, and it goes smoothly, in this direction. And example of this discriminatory function is just sigmoidal function, as you know, Okay, and so if this function is fixed, and parameters, weights are, arbitrary real numbers, from actually 0, 1, then this hypothesis set is dense in the set of continuous functions, on this domain, actually. What does it mean, dense? Dense, and this is important, dense means that for any continuous function, we can find function represented in this form, or, in other words, computed by a certain neural network, such that their difference, but difference, is in the space of continuous function. It's not square mean difference. This is a big difference, actually. So this is a so-called supremum difference. Can be as small as possible. So okay. Actually, this this difference which I stressed, in optimization, is how to say, is helpful for uniqueness. We can find unique solution with the help of this. Measure. This is actually a norm. In the space of continuous function, but it does not mean that the same solution. Is unique in the space. With least square norm, so you shall also, so uniqueness is here, but not in this space, but also we know that learning of neural networks is based, of minimization of square root difference, so this means that again, so it'll pose problem, but nothing to do, Okay, so this is, yeah, some remarks, yeah, which actually I explained that. And, yeah, and here you see the estimation, yeah. So if we have only capital N unknown, capital N known data pairs, actually, yeah, then the number of parameters, as you see, is n multiplied by small n plus 2, and where small n here, so now I forgot, so something, one n is the number of inputs, and another n is the number of neurons, yeah, actually, yeah, so probably it's vice versa. But in any case, it's much bigger, yeah, than input data. Okay, so yeah, so this is also, yeah, on the basis of coincidence of expressions which are marked by 1 star and by 2 stars, yeah, we make a conclusion that what is computed by a neural network of this configuration, yeah, is expressed, yeah, I mean, as a function in our hypothesis set connected, yeah, with this neural network. Yeah, so, and again, the consequence, yeah, you can read it, that this hypothesis set is dense, and we expect, yeah, to find a good solution. Okay, so, yeah, now we will be focused how actually this optimal solution can be found, yeah, and to answer this question, yeah, we shall first of all understand semantical meaning of all parameters, yeah, and actually, you know, so yeah, now I propose you to do this manually, yeah, because you know, so we cannot explain to nobody how any machinery works, yeah, without performing the computation manually, I mean by hands actually, yeah, with paper and pen actually, yeah, and then being focused on adjusting parameters, let us think. So we have neural network, yeah, with the configuration which I explained, we have data. How we can select parameters such that this neural network computes exactly the given data set. Okay, so yeah, this means that we shall analyze the meaning of parameters. Yeah, so this is my main goal today. Yeah, actually, yeah. First of all, meaning of the activation or function, we will select sigmoidal. Yeah, look. So on the left image, yeah, we see this sigmoidal function. Yeah, on the I mean, with the range, yeah, from 0 to 1 on a certain domain, yeah, so from minus to plus, yeah, actually, it's not restricted, domain is not restricted, yeah. Okay, so, and then we are working, so here you see the expression of activation with 2 parameters, weight, W1, this is input weight, we remember, and bias, yeah. And if we constitute, if we apply these parameters into the expression, we will see how the expression changed, yeah. And now, what is the influence of these parameters? Yeah, look at the input. So the first image shows this function with parameters once, so actually no parameters, yeah, actually once they are neutral, yeah, with respect to this computation. But if we enlarge, yeah, so you see, so if we use input weight as 1000, yeah, and bias minus 200, then our activation works as a step function, actually, yeah, practically, no difference, yeah, this is image, yeah. And moreover, so it is step function, and we shall know where step is. And step is computed, yeah, you see the expression. This is the expression that connects bias with input weights. Just, yeah, this is semantic meaning. So we know that if we increase the input weight, we decrease the smoothness area, yeah, I mean between discrimination between 0 and 1. Okay, so let's fix, yeah, this information. Now, another, the step, the height of the step. Before, it was 1. So, can we enlarge the height of a step? Yes, we can. And we can do it by increasing the output weight, yeah? So, you see output weight, 1.5, yeah? And it is responsible for the height of this step. So, now we know, we have step. And we know how to compute this step. I mean, yeah, the point where the discrimination actually is performed, yeah, and then we know how to assign a height. Okay, so let's use this information and ask the second question. Yeah. Okay, so is it possible to compute very primitive function, yeah, using this information? The answer is positive, yes. And as a primitive function, yeah, we selected so-called tower function. You see its image, yeah. And actually, in order to compute this tower function, yeah, we know everything, yeah, because this is combination of two steps, yeah, one against another one. So this means that, yeah, so weights, yeah, input weights are the same because they are responsible for steps, yeah, and then step node, yeah. So we know that bias, yeah, is responsible for that. So we assign bias, yeah. And actually, because you know steps are at different points, yeah, biases are different, yeah. So minus 200 for the left and minus 300 to the right, yeah. And then you know, so output weights, yeah, should be of negative signs, actually, yeah. In order to work against, yeah. And actually putting all things together, yeah, the height is 0.6 and this height is just the height of our tower, yeah. So this means that we managed, yeah, so we know function, yeah, primitive function, yeah, and we know how we can assign parameters in order to compute this function. Okay, so now let's do this, yeah. Now we have any continuous function. Yeah, and actually we first approximate this function using a certain number of steps of tower functions, of elementary. We put tower functions together, yeah? And actually each tower function, yeah, we remember, is computed using 2 neurons. In this case, we have approximation with 1, 2, 3, 4, with 4 towers, and this means that our neural network, which we can associate, should have 8 neurons, yeah, double of, in comparison with the number of towers. And so this is the architecture, yeah, and of course, yeah, so if we want, because we remember, Sebenko theorem, yeah, states, yeah, that any continuous function can be approximated, so we know, so first of all, we approximate using a system of towers, and then each tower is just represented using a tower function, and immediately we have the construction of a neural network which really computes with this certain error. Error can be somehow computed from this tower approximation, yeah, and so we have the result, yeah, so look, yeah, it looks nice, yeah, actually, yeah, and this is computed by a neural network, yeah, with, which has, yeah, capital N is the number of neurons, yeah, just keep it in memory, with 100 neurons, yeah, it means how many towers does it have, yeah, okay, so I will be, yeah, okay, so there is another learning paradigm, yeah, which is also a focus, yeah, of our, yeah. So as we learned, yeah, so we have too many parameters, yeah, actually, yeah, and the parameters, yeah, they, how to say, they are against uniqueness of a solution. And therefore, an author, yeah, so his name is so Chinese, Huang, proposed another learning strategy. Okay, what if, yeah, we make some parameters randomly selected, actually, yeah, weights, and he proposed, yeah, to input weights and biases, yeah, to be randomly selected, and only outputs, yeah, are computed according to the theory he proposed. Yeah. Actually, he uses the same model. Now it is labeled with 3 stars, but it is the same with the previous one. And there is only one unknown vector, and this is vector of output weights. So the notation is different with beta, yeah, actually, yeah. And so we make random selection and compute only this. How we can compute? So this is the algorithm, actually, yeah. So I will not read, yeah. Actually, when we randomly select parameters, we have matrix that connects inputs with outputs. In this matrix, actually, it's not necessary square matrix. Normally, this is orthogonal or actually rectangular matrix, and therefore, it cannot have an inverse, but it can have a so-called pseudo-inverse. And he proposed, yeah, to make computation using this pseudo-inverse matrix. Okay, so, and this is the point, yeah. So it looks, the theory looks really, yeah, well-founded. There are many papers, there are many follows, yeah. And when we thought about how really it works, yeah, so we decided, yeah, really to analyze, yeah, about stability, yeah, actually, yeah, stability of this pseudo-inverse. Pseudo-inverse is not inverse, but even it has an inverse, yeah, it depends heavily on the discriminant. And when discriminant is close to 0, the computation is not stable, actually, yeah, and actually because, yeah, you know, neural network, yeah, is made on computation step by step, it makes rounding and other things, so it leads that nice theory, but bad realization. And I will show you, yeah, so the question is, should I trust, yeah, this learning? And actually we proposed, yeah, the so-called counterexample. So we created this sample. As you see, the sample, yeah, is a combination, is a union of two sets, yeah, actually, yeah. So they are not computed at the same points. They are, the points are similar but different. And actually, you see, when we applied the algorithm, yeah, of this ALM, this extreme learning machine proposed by Huang, the result is 0. It's green line, yeah, yeah. Actually, yeah. So nice theory, bad result. Yeah. So this means, according to our explanation, that the model, I cannot say that it is bad, but it is not good. And this means that we shall think about assumptions, yeah, and actually they are not in the algorithm. Okay, so yeah, this is, yeah, so this is also I explained, so bad model. Okay, but now we ask the question, okay, so if we cannot compute this type, I mean, of sample, yeah, using the approach of extreme learning machine, probably there is no any neural network for performing this computation. But the answer is negative. It exists, yeah, and actually to show that it exists, we follow the procedure which with towers, actually, yeah. So we first connected all points, yeah, with straight lines, yeah, and then we applied the procedure of towers. And here you see the results. But we remember, if we have n training pairs, the number of towers is twice. So for 20 input-output points in our data set, we used here 400 hidden nodes or hidden neurons. Okay, but as you remember, probably I didn't focus you, yeah, but the theorem of Huang, yeah, proposed that there is a network with exactly the same number of hidden neurons. So we have 200 input-output points, yeah, so we expect the existence of a neural network, again, with 200 nodes. It cannot be done, yeah, with the help of the procedure proposed, yeah, with this rectangular approximation. But we have the theory, which I explained you in my previous talk on the Infus conference, and this is the so-called F-transform theory. Of course, yeah, I do not want you, yeah, to remember all the details, but actually, if we use this theory, this is, yeah, no, so this is fuzzy modeling, actually, yeah. So we created a neural network which exactly computes, yeah, this sample and uses only 200 hidden neurons. Yeah, so this is actually, yeah, our contribution, yeah. And according to this, because now we know how it works, we actually manually adjusted parameters, so we can explain. And here you can find the answers to the question, yeah, you remember, 4 questions, yeah. So I repeat and answer. What can be learned? Any continuous functions, we know. How many neurons? The same as we have, yeah, in our sample. How does parameter assignment affect proper learning? So if we respect semantics, and semantics is as follows. The input weights, yeah, they determine the size of the corresponding cluster, yeah. So I will not go into the details, but you can imagine, yeah. So input weights, they control smoothness. And smoothness actually is connected with the size of a cluster, yeah, nothing special. Then activation function determines the shape of a neural cluster. The bias determines the center, yeah, you know, step function, yeah, should have center, it is bias. And the output weight determines the corresponding value of the function. So that's it, yeah. So, and if we respect this meaning, then we will be, you know, we can believe, we can trust, yeah, in our neural network, and this is important, yeah. We have a model, we know how it works, we can make prediction, and also we can explain how it works, and this means that, yeah, if we, with conscious, yeah, approach, yeah, to the design, yeah, so we really can prove that the result will be efficient. So that's actually all, yeah. Thank you for your attention. You know, this is a very good question, yeah, but however, yeah, I cannot give you an immediate answer because actually, yeah, as I tried to explain, yeah, so this activation function, yeah, it actually, it works, yeah, how to say, yeah, so look, when we are based on nodes, yeah, on samples, yeah, but then we create model that have these samples, yeah, as say nodes, yeah. So this means that the domain of our model is wider, yeah. So this is actually something like compact set, yeah. However, these data should be separated. This means that in this domain, yeah, around each given node, yeah, from a sample, yeah, we shall create, yeah, something, yeah, I mean some space, yeah, and actually, yeah, in F-transform approach, yeah, we did it, yeah, we just put fuzzy set around each node, yeah, such that this fuzzy set, yeah, I mean separates this node from neighboring nodes, yeah, and this means that, yeah, how, you know, so I explain in words. Technically, this fuzzy set, yeah, is combination of certain activation, and in this case, activation is a bell-shaped function. It's not sigmoidal at all, yeah. With sigmoidal, yeah, we can work using this a la Sebenko, yeah, approach, because, yeah, sigmoidal requires opposite sigmoidal, yeah, in a certain sense, yeah. With bell-shaped activation, yeah, it works more efficient, actually, yeah. And this is the answer to your question, yeah. Thank you. Yeah.
Can we trust the neural network to simulate the extreme phenomena as floods? So,
you mean which phenomena?
Extreme phenomena. Like floods and so on.
Yeah, so yeah, it's a very difficult question actually. Yeah, so you know, actually my example, yeah, I didn't connect them, but I can actually. Yeah. So look, remember husky and wolves, yeah. You know, so the point is that in separation, yeah, actually, yeah. So we actually how neural network works, yeah. It extracts so-called features, yeah, actually, yeah. Features are just coefficients in any regression model, yeah, which somehow characterizes behavior or element from hypothesis set, actually, yeah. And, yeah, you know, so what is important? It is important that you know, so I stressed the criterion, yeah. So if we work, yeah, in this space with supremum, I mean norm, yeah, then it allows us to separate very close objects, yeah, functions which are closed. Yeah. However, when we work with least square mean criterion, yeah, it creates a kind of circle. Yeah? And this means that there is no unique solution. We cannot find. We can find solution which is close, actually. Yeah? Yeah? And this is the point, actually. Yeah? So because in your example, yeah, the separation should be very precise, actually. Yeah? Because, so probably, yeah, if we are thinking about time, yeah. So when what is the time when floods actually are dangerous, yeah, for us? And we shall be precise. This means that the separation should be very, very precise. And this means that actually, probably this manual approach, yeah, which is based on supremum norm, yeah, is better actually, yeah. Or we shall combine, yeah. So we shall combine pre-processing with the processing available. In any case, technically, it's really complicated.
Thank you very much.
Thank you.
I would like to give this certificate to you.
Yeah, thank you.
You to just
Okay.
okay. Thank you. Okay. Our next invited speech is from Professor Klasimir Atanasov. He's a very well-known researcher in fuzzy logic. He has been cited more than 43,000.
Do you hear me?
Yeah, sure, we can
hear
you.
Just a second.
Just a second. I can't hear. I do not hear presenter.
Okay, right now, can you hear me?
Yes.
Okay.
Do you listen me?
We can
yes,
hear
I hear you. I hear you.
Oh, great.
Now.
Okay.
Okay. To start, or
Just
there are some problems. In some moment, I cannot
okay.
listen anything.
Let me introduce you, and then I will.
Can I start already?
Okay. Sure. Sure. You, I think, yeah, okay. So, can you present? I stop my presentation. You should be able to present now. Professor Atanasov.
Do you listen me?
Yeah. Now we can see. Perfect.
Yes, everything is okay.
Okay. To start the presentation, yes?
Yeah, sure. You can start the presentation.
Oh.
We can hear you.
Must I start already?
Yeah. Yeah. Yes, you can. We are ready. We are listening. Hi. Professor, can you hear me? You can start. We can hear you. Yep, sure, you can start.
Добре. Съвсем чувам, аз питам няколко пъти.
Professor Atanasov, we can hear you. You can start if you want.
Дай да го сменим. Може би...
Can you send a message? No? Okay. Okay. Can you hear us? Hi. So, Professor Atanasov, let me introduce him meanwhile, while he's trying to solve his technical issues. He's the head of Department of Bioinformatics and Mathematical Modeling in Bulgarian Academy of Sciences. He is also an adjunct professor at Raffles Institute in Sydney. He is a fellow of Fuzzy Systems Association. And in the fuzzy sets area, he has invited intuitionistic fuzzy sets, which is commonly used. He also, in the pattern nets area, he defined generalized nets, and in the number theory, he also proposed the Fibonacci sequence generalization. He is an editor-in-chief in many journals, including Notes of Intuitionistic Fuzzy Sets, Advanced Studies in Contemporary Mathematics. And he is the member of boards of many journals, including New Mathematics and Natural Computation, Bioautomation, and so on. And today he will have his speech on new results on extended intuitionistic fuzzy index matrices. Professor Atanasov, can you hear us? I cannot see him anymore. Professor Atanasov, can you hear us? He's not in the... Okay, I think he's having some technical issues. Meanwhile, I would like to ask a question to Professor Irina. So, after? He's coming. Okay. So, last year we discussed it, and today you also showed us how fuzzy logic can be used in this machine learning. And what do you think for the future? Do you think that fuzzy logic will be used more in this new artificial intelligence era? Will there be more fuzzy logic in the future, or does it have a limited, usability?
Yes. So thank you for the question. To continue our discussion. The role of fuzzy logic, actually, in neural network computation. Actually, so my opinion is that there is no logic, actually, in this type of computation. And as I started, my presentation, so we shall learn different language, actually. Fuzzy logic, distinguishes from other areas, by its language, And for years, the language was based on theory of algebraic logic, on special connections, which are, more taken from the lattice theory than from the theory of, continuous functions, of real-valued functions, whatever, And actually, when I worked on image processing, I compared technique. Actually, what we did, we worked with the so-called compression reconstruction of images. And actually, the compression can be made using fuzzy logic, in general saying, connectives or operations that are similar, to logical connectives. And then the compression can be made also with the help of, we call them arithmetical operations, and they are based on summation and multiplication and related operations. And the results, actually, so with the help of logical, fuzzy logical algebraic operations, we are able to make a reconstruction in a certain corridor. Yeah? So we are able to compute lower bounds and upper bounds, yeah, of our reconstruction quality. But with the help of arithmetic operations, yeah, we are always, yeah, I mean, in the center. Yeah? So this means that, yeah, this means that the efficiency, yeah, of the same technique, which is based on arithmetical operation, yeah, is much better. I mean, you know, so yeah, I shall be precise, actually. You know, everything is a matter of complexity, actually, yeah. So we can really, yeah, so as I said, yeah, we can make reconstruction, but we have corridor, lower and upper. But of course, yeah, adjusting parameters, yeah, we can make this corridor as narrow as, you know, so we are able, yeah, to have it, yeah. However, it requires very complicated processing, actually, yeah. And actually with real numbers, with arithmetical operation, we are not required, yeah, you know, to be focused, yeah, on narrowing corridor, because we are always, yeah, you know, in the center, yeah. That's my answer. Okay, so yeah, actually, you know, so fuzzy logic, fuzzy computation, it's a matter of taste and it is a matter of training. If so, you are trained, yeah, and if you are not afraid, yeah, of complicated work, so you have green lights, yeah. But you know, so yeah. Classical mathematics based on, you know, stable machinery is, in any case, more efficient. Moreover, criteria, you know, so we, you know, so when we try to publish our results, we shall respect criteria, yeah. So any known criterion is based on least square error, yeah, or things like that. And therefore, in order to minimize, yeah, using again algebraic operation, this is very difficult problem. Yeah. So therefore, yeah, but I do not want to say that forget about fuzzy logic, not at all, because yeah, you know, so also, so the theory which I'm trying, yeah, to push forward, this is so-called the fuzzy transform technique. Yeah. It is based on the ideology of fuzzy sets. Yeah. But computation is based on classical mathematics. So this means that the answer to a question, yeah, the proper combination, yeah, of, you know, so logical approach, yeah, which really respects semantic, yeah, with computation based on technique, yeah, which really proved its efficiency through years, yeah. This is the optimal solution.
Thank you very much.
In the continuation of this discussion, I also have this kind of the opinion, like, you know, if we introduce the fuzzy logic in field of neural network, so Madam has already discussed the thing, like, you know, how the things depends on the mathematics. And in fuzzy set theory, we have the entirely different concept. Like, you know, we have the different definitions of fuzzy metric space. We have the different definition of Cauchy sequence. We have the different definitions of this, you know, limit pointers, all those stuff. So if it is introduced, of course, the complexity of the neural network will be increased, but that will be the different era of this neural network. Okay. And in the continuation of that questions, what exactly the problem is that, like, you know, why we assume this kind of a thing that, you know, the problem and the solution should always be the member of the same space. What will happen, like, you know, if the solution is coming in the neighborhood of that point? Like, you know, my question, the question which arises in the mind, like, you know, the concept of this totally boundedness and boundedness kind of the things. If these two conditions are relaxed, then, you know, we are giving the liberty to the system to have the solution little away from the problem domain.
I think this is a very interesting, you know, discussion, and let's make it during the lunchtime. Professor Atanasov is waiting, and we are going to start now. I think this is, we all want to talk and discuss right now. I'll see you at the lunchtime. So, Professor Atanasov, you can start now. Hi. He said he is ready now. He's ready for the presentation. Professor Atanasov. I'm still waiting. Oh. Okay. Okay. Hi, we can see you. Professor Atanasov, can you hear us? Okay, okay, sure. Thank you. He can start if. Okay. He needs to open the microphone. His microphone is closed. He needs to.
Professor, do you hear me?
But no. He has to open the microphone. Actually, his microphone is closed. Yeah, we can hear you.
Okay.
Now,
Okay.
now we can hear him.
Okay, I am very sorry for all problems about my presentation. As I thought a minute ago, my spoken English is very bad. Excuse me about it. Okay, in my presentation, I will tell shortly about new results on extended intuitionistic fuzzy index matrices. The concept of intuitionistic fuzziness was introduced in 1980 year, and only year after this, the concept of index matrix also was introduced as extension of the concept of standard matrix. For example, when we have two matrices with different dimensions, we cannot realize operation addition over them. But there are a lot of cases in which this is important to be realized. And by this reason, in 1984 year, I introduced the concept of index matrix, and later it was extended to intuitionistic fuzzy index matrix and to extended intuitionistic fuzzy index matrices. All results of mine were collected and published in a book in 14 years, and during the last 10 years I received some new results in this area, and now I will tell about some of them. Firstly, I will mention that the concept of intuitionistic fuzzy set is the following sense. When we have some universe E and its subset A, then the intuitionistic fuzzy set A has this form, both degrees mu and nu are degree of membership and degree of non-membership, and they satisfy this inequality. Over intuitionistic fuzzy sets, a lot of operations, relations, and operators were introduced. Two of them that we will use now are operators that are modification of standard topology operators closure and interior. Intuitionistic fuzzy pair is object with the form AB, where A and B are elements of interval 0, 1, and their sum is also in this interval. And they correspond to degree of membership and degree of non-membership. Over intuitionistic fuzzy pairs, different relations and operations are introduced. Now there are more than 200 different implications that generate more than 50 different negations. This negation in practice is the classical negation, but a lot of other negations are non-classical. Some of them have intuitionistic fuzzy intuitionistic properties. A implicate not A, but the opposite is not valid. And some of negations have the opposite behavior, not A implicate A, but the opposite is not valid. Now about index matrices. They are standard matrix, but the rows and columns of which are indexed by indexes from some fixed sets of indexes. Elements can be elements from the set of real numbers, but they can be elements of, for example, logical variables, can be intuitionistic fuzzy pairs, and others. Most important is that now operations over index matrices are not related to places in matrices, but they are related to the pairs of indexes, and by this reason, in particular case, we obtain the standard matrix operations, but over index matrices we can introduce some specific operations, relations, and others. When elements are intuitionistic fuzzy pairs, then we obtain intuitionistic fuzzy index matrix. And when indexes also have degree of validity and degree of non-validity, then this matrix is called extended intuitionistic fuzzy index matrix. In this case, degrees as of the elements of matrix, as well as the elements of the indexes, alpha and beta elements, they must satisfy these conditions. They must generate intuitionistic fuzzy pairs, and therefore the sets of indexes generate intuitionistic fuzzy sets. When we have two extended index matrices, then we can introduce different operations over them. For example, operation addition now has this form. In the result, we obtain new index matrix that has indexes, as I mentioned already, they will be intuitionistic fuzzy sets. And now, when we have this operation, we over indexes apply operation that stay on this place. In the standard case of standard matrices, when here stay operation addition, this is operation over the two matrices and respectively over their elements. In this case, this operation show that the operation will be addition over matrices, but over level of elements, we must realize operation that is shown here. This is for indexes, and this is for the elements of matrix. We see if the set of indexes for different the two matrices are different, then in one case we bring the intuitionistic fuzzy pairs from first index matrix, in other cases for second index matrix, and only when there is coincidence of the indexes of both matrices, then we must apply the operation over the components of these matrices. Now we can see that when both index matrices have equal index sets for the inputs and outputs, then this set, respectively this and this sets, will be empty sets, and therefore we obtain only this case that correspond to standard matrix operations. But operation in this case addition. But in index matrices we can obtain other situations that don't exist in the case of standard matrices. Similar is situation with operation term-side multiplication that is used in combinatorial analysis. In this case, we bring the intersection of indexes of both matrices and operation over the elements that stay over the equal places. Operation must be this operation that is shown as a second index of the operation over index. The case of multiplication, standard multiplication, also is in such form that in particular case give a result of multiplication over standard matrices. But again, there are some situations that don't exist in the case of standard index matrices. Now, first operation is over indexes of the result matrix that is obtained in a result of operation, and now this is the result of application over the element of matrices. So when we have operation, first operation is addition and second multiplication, then we have sum of multiplications of the elements that correspond to operation multiplication over standard matrices. But now on this place can stay another operation, for example, conjunction, disjunction, addition, subtraction, and here must stay another, the same or another operation. And by this reason, this operation has essentially more possibility for representation of different operations over matrices. Now, I must tell that over index matrices, different other operations as reduction, projections were introduced, and they can be transformed directly over extended into tunistic fuzzy index matrices. But these operations cannot exist, cannot be applied over standard matrices. Over standard matrices, we cannot introduce relations, but here this is possible, and now we will discuss 8 different relations. The relation strict inclusion about dimension has this form. Matrices, first matrix is included in the second, A is included in B, and the joint elements of both matrices coincide, but in B can exist elements that don't exist in A. If these inclusions are not strong, then the relation already is not strict relation inclusion about dimension. Relations strict inclusion about element values has this form. Now both matrices coincide as dimensions, as indexes, but elements of first matrix are smaller, strongly smaller than elements of the second matrix. When the relation is not strict, then this inequality is valid. The strict relation inclusion about fixed index values has this form. In it, the both matrices coincide, but the intuitionistic fuzzy pairs related to first indexes of the matrix A are smaller, first component and second higher, than the intuitionistic fuzzy pairs corresponding to the indexes of the second matrix. When the relation is not strict, then these strong equalities are changed with these equalities. And similarly, we can introduce relations strict and non-strict relations over second indexes of both matrices. Now, we will discuss other operations that can be applied over over one intuitionistic fuzzy index matrix. Let us have it, and then we can change the index K that has intuitionistic fuzzy estimations, degree of validity, degree of non-validity, this with the same index but with different degrees. In first case, this index is for first index set, now is for second index set, and this can be modified extent for the case when we change both indexes in rows and in columns. More general case is, second possibility is to change the index together its evaluations with new index and with new evaluations. And this is for the case when index is for first set, with are marked the rows of index matrix, and second operations is over indexes with are marked the columns of index matrix. This can be extended to the case of change of indexes of rows and of columns. And after this, we can construct more complex formula. Now we can see that this is that the result of applying of this substitution over the opposite substitution does not change the form of index matrix. Also, we can extend these constructions when we have a set of first indexes and set of second indexes with which we to change the existing indexes of the given index matrix. And in a result, we obtain this. We obtain a new index matrix with a respective change of their indexes. Now we can see that these substitutions don't change the form of index matrix. When change set of first indexes with another set, and after this second set with the first, or with the second indexes, the result will be the same. And we can prove also this theorem that change of indexes of rows with another set of indexes, respectively indexes of columns with another set of indexes. And after this change of these sets with other sets, in a result we obtain index matrix with second types of indexes. Finally, for element K from indexes of rows and element L from indexes from columns, we can change the element that stay on the cut row and out column with to obtain new truth value. And obviously this change will keep the form of index matrix where this element is stay on place key L initially.